Hello, Science 24. Today we're going to be talking about reactions and the environment. This one is the last chapter in Unit A, so the last little bit for chemistry. And remember, this is the final chapter before the unit test for all of chemistry. So take good notes, make sure to review key terms, and we're starting to study after the end of this for our unit test. We want to start this chapter by talking about something of a little bit of history to Canada and how chemistry has been used in the past, because we've been talking about chemistry in the past and now. And this one is a great example of how chemistry and when chemistry goes bad. To set the scene, if you look at the date here for the Halifax explosion on December 6, 1917, that is right in the middle of World War I. What was happening was Halifax was used as a major Canadian port to help the war efforts. And so it was a gathering point for lots of materials and to ship troops and those materials out towards the European nations facing that war. What happened was there was a boat collision, and that boat that was involved in the collision was carrying munitions. And as I was kind of watching through some of the videos for this and reading about some of this stuff, it was carrying a lot of ammunition supplies and a lot of different chemicals. All these chemicals added up to an extremely large explosion. This has been noted as one of the largest pre-nuclear explosions to ever happen, and the shock waves were felt for kilometers away. Here you can see from this image is a YouTube video that I found, and it's called A City Destroyed, the Halifax Explosion. And if you wanted to look up on YouTube this video to watch, please do, because it gives a quick overview of what exactly happened, and they kind of set the stage for, well, how does a shipping accident like this happen? And why was it so bad? So it's a good little video. If you wanted to flip out of this video and pause and YouTube search this one, please, just to get some background. It's kind of a helpful one and explains it much better with cooler graphics than I can. From the video, you probably saw about 4 of these things they mentioned and what made them so dangerous. Well, probably you've heard of TNT and how explosive that is, and that was one of the big things that caused this explosiveness. However, some of the other things that you might not have ever heard of was something like picric acid, where this is a highly volatile substance that when kind of jostled and when shaken, it explodes quite quickly. Gun cotton and this benzol, as you can see, well, these are part of the fuses, and they're the things that burn extremely, extremely fast. They're not necessarily explosive, but they accelerate how fast flames can travel. And just like a fuse, well, it makes it travel very fast, it burns, gets hot enough for the more dangerous things to heat up and then become a huge, massive explosion. And so, unfortunately, this boat was carrying all of these highly flammable, highly explosive materials, and when it got hit and a little spark happened, well, the things that are highly flammable catch on fire. And when that fire starts burning and burning and it gets hot enough, it sets off the explosives, creating this massive, and I mean massive, explosion that is on the levels that was only beaten by nuclear explosions. So while that explosion happened over 100 years ago, we also want to just come back to what we're learning about now and how do we know when a combustion reaction actually happens? And for one of the good examples is, hopefully I can include a lab video once we kind of get back to it all, is a candle lab and how we could just see a candle. How do we know something is burning when we look at a candle? Well, you're probably thinking right away, well, it's lit. Well, of course. Seeing the flame, seeing the fire is one evidence, but what else is there for evidence? And if you were ever to hold a beaker or some kind of flame-proof material over top of the flame, you'll see that it'll start collecting moisture on the inside. If you hold it over the flame, it'll start creating smoke and soot. Just like when you blow it out, you see that trail of soot or that smoke coming off of it. All those things are evidences of the chemical reaction, that combustion is happening. So here we're going to look at what a combustion reaction is. And when we're looking at it, we want to see fossil fuels and their combustion. So anytime, please make sure to pause the video, copy down these examples as we go if there's not enough time. But you can see here, when we're burning gasoline in a car, we can have our equation or our word equation to read what is actually happening in the reaction. And we can see with any combustion reaction, we're having oxygen burning in the presence of some kind of fuel, and this time it's octane, and we're always going to produce carbon dioxide, water vapor, and we're going to get that energy, well, and we know what the energy is used for in a car, to make it go very, very fast. We're now going to expand on that combustion because, like I talked about in that candle lab, if you held a beaker over top of that flame, or if you held something over that flame and you started to not allow enough oxygen to mix in, or if you don't have enough fuel and it's just not burning properly, and it's not burning hot enough, not burning complete enough, we're going to get incomplete combustion. An incomplete combustion is where we get extra products being formed. And we're going to have these extra things like carbon and carbon monoxide being formed. And this is when it becomes an issue. And we can see the general formula of, oh, all of a sudden we're getting a lot of extra things being produced when we don't have enough oxygen to actually burn the fuel source enough. So this became a big issue when we started to look at the world. And when we started the Industrial Revolution, when we started burning all this coal and all this fuel to actually heat up and create steam and run different types of engines, we created a lot of carbon monoxide and carbon because really it's very, very hard to have a complete combustion reaction. And most times we're going to be having an incomplete combustion because most times a fire gets so hot it can't actually take in enough oxygen to burn fully. And so we always get these byproducts. Even the most fuel efficient cars, as soon as they start running in an area, they're still going to produce carbon soot and they're going to produce carbon monoxide, just at very, very small levels. Way back when things were not as technologically advanced in the Industrial Revolution, when they're still figuring things out, they definitely produced a lot of extra carbon. And so here is the climate change caused for over 180 years ago. So if you YouTube this, it's a cool little graphic video to highlight how we've kind of changed from that Industrial Revolution 180 years ago to now, and what was the effect from these hydrocarbons. And as I was finding different videos to watch, I found this one. It was kind of funny. This is from one of the ones I like to subscribe to. This is from Kyrgyzstan. But again, search up on YouTube and there's lots of good little videos. Always take it with a grain of salt, meaning always make your own opinion. Don't just take everyone's word as scripture. But what you see is who's to actually blame for all of this? Who's responsible for climate change and who needs to fix it? Because shouldn't the people responsible be the ones to fix it? This video brings up some interesting points to think about, and it's not so easy, making climate change and this environmental talk so complex. While climate change is a very, very hot topic issue, and it's very hard to kind of talk about who's responsible and who's not responsible, I do want to talk about some of the actual concrete science that we do have. And so what we know about greenhouse gases and this greenhouse effect is, well, we need it. The issue that rises up is, are we increasing this greenhouse effect? Because as you can see, there's greenhouse gases, there's CO2, there's water, there's CH4. But from here, we need this effect because the sun will come in, it will hit the land, it'll hit the ocean, and it will change from light energy into heat energy. And when that heat energy, it doesn't just travel through our atmosphere the same. And so it actually gets trapped with the CO2 and the CH4 or that methane. And so we essentially trap that heat energy because it's been converted. This is important because this keeps us about from like a plus 15 average global temperature. Instead, if we didn't have it, we would be like a minus 18 global temperature, and we just couldn't live that way. With this greenhouse effect, it creates a stable climate for us. The issue that everyone fights and debates about is, are we increasing it? Because are we increasing these CO2 levels right up here? And if we have more CO2, so if I was to put more CO2 in here, that means more trapped heat. If we're putting more methane in, because a big responsible fact for methane is livestock and cattle and just having these particles up in the atmosphere, well, that's not so good. So if we're trapping more, that means we're getting warmer. And that becomes the issue, is we're trapping more and more heat and we're getting warmer and warmer. And this climate change is we're seeing these more irregular weather patterns pop up. And then the debating starts. So the greenhouse effect gets its name aptly from a greenhouse. A greenhouse works because it allows the light to come in and it keeps the area a lot warmer than the actual outside surrounding area. And it'll actually keep it nice and warm and moist, and it'll allow lots of light in so plants can grow, and it'll be warmer so again the plants can grow and not freeze in colder areas. This is great because the sun's shorter waves, as you can see blue coming in, hits the areas. The short waves hit the ground or it hits the plants, and then it gets converted into thermal energy or this heat energy, and it can't actually pass through the glass, so it actually gets trapped in there, creating a much warmer area than the surrounding air temperature. The longer waves, as you can see, still can escape, and so really long wavelengths like radio, if you wanted, can still escape and bounce out, but the infrared gets trapped in there. And here I just gave the notes and the details in case you missed it as I was talking last slide about the global average temperature, and then the debating that happens about what happens if we go up 1 degree, or what happens if we go up 2 degrees. How does that change everything? Here I would like to have a class discussion, and depending on the time frame of it, we will see. But right now, what are your thoughts about climate change? And so give each question a quick little thought or think through as they pop up. So what else have you heard about climate change? Have you heard any other details, or am I just spinning lies? What is there to do about it? Like, what could you do, or what is happening about it? Can you change it? This comes up a lot. Is climate change a giant hoax? Is it just trying to lie to you and scare you? Or what is there that you can actually do? What about all this environmentalism? Is it a good thing, or should we just be reckless with it? What can we actually do? Now we're going to dive deeper into some of the other effects of combustion reactions. So we talked about climate change, and we talked about the greenhouse effect and the release of CO2. There's also some other products, and again, like I said before, there's not just gasoline or there's not just a hydrocarbon in fossil fuels. Sometimes there's other things that have been put in there, just how they were when we got them out of the ground, and they lead to other air pollution. Some of the big ones are sulfur oxides, so it could be like an SO2 or an SO3. And then there's nitrogen oxides, so an NO or an NO2. And this is just happening in the air because sulfur can just be present in the hydrocarbons and it can't get completely burned out. Nitrogen, 70% of the air is nitrogen. So when you're burning things in oxygen and air, well, some of that nitrogen gets trapped and gets caught up in that combustion reaction as well. What happens is, well, you might want to copy this and pause the image as we talk about it. So if not right now, pause it and we can copy it down this little image. Well, what can happen is this happens naturally. Sulfur and nitrogen get released naturally. The issues, though, is what you see at the top is those reactions where this sulfur dioxide, but there is NOSO3 as well. But for the most part, this sulfur dioxide gets released from forest fires or gets released from volcanoes, reacts with the water in the clouds, and it turns into sulfurous acid. Same thing when things are burning in open air and this nitrogen gets caught up. This nitrogen reacts with the water in the clouds up in the air, and it turns into nitric acid. And you can also get nitrogen monoxide gas, which is very dangerous. And then when we get these acids in the cloud, we're having acid rain. What can happen then is, well, we can also accelerate this. And as these compounds fall, we're getting acid rain. And you can see by the clouds, they don't always just fall where the factories are, they get carried through the air. And so if there's nothing in the air, no water for it to react, it can just fall as dry deposition. And then it just has these little compounds on the ground. And then the next time it rains, well, there's still your acid rain wash off. This is the issue because, well, it can be human caused, and we see that through factories and cars burning, we accelerate this acid precipitation. So if you remember, we talked about acid-base reactions from chapter 3 when we saw neutralization reactions, and these reactions happen all over the place. They happen in our body with stomach acids, and we have hydrochloric acid, that's our stomach acid. But when we take an antacid, like sodium bicarbonate or just baking soda, or we eat like a Tums where it's calcium carbonate, we neutralize some of that acid to suppress that heartburn. Or when we eat spicy food and it's upsetting our stomach, we can balance out that acid-base reaction in our bodies. This can also be applied to the environment to counteract some of this acid precipitation though. We can use this to our advantage when lakes and water systems become too acidic, or like I said, when all this dry deposition, when it gets carried just in a gas cloud and it just falls as kind of just particles and it falls on a farmer's field, and then when it gets irrigated or watered on, it turns the soil very acidic. Well, we can use this process called liming to actually add chemicals to help neutralize the acidity, because a lot of things in the water systems or plants, they can only grow in a very specific pH range. And if we don't take measures, it can really affect crops. And I like that one picture with the farmers where they're comparing the pictures of unlimed versus limed treatment to really help stimulate plant growth. And you can see how they can add it to water systems or how farmers can actually spread this calcium carbonate just like a chalk to help neutralize it. So that neutralization, that liming is one step, but it's not really problem solving. It's just a solution. It's just kind of temporarily fixing it and patching it. It's not stopping it. One of the things that does stop it, because we know it's so dangerous, is we actually can remove sulfur from natural gas, which is called just sour gas. And it's kind of funny that they call it to sweeten it. They remove the sulfur before they're actually burning it. And so they can do this so we're not just putting the sulfur dioxide into the atmosphere. And so we're actually stopping the acid rain. And so we do this, you can see it's called a sulfur scrubber, and it's captured after it's burned by a process called scrubbing. And so instead of releasing it as they burn it, so you can see it enters in through here, and instead of adding limestone to it as the after process, they add it in there, and before they exhaust it, they collect all the heat, and before they exhaust it, they rinse it and they bathe it in a limestone mix and a big slurry, and it captures all that SO2 and it turns into acid rain in this chamber, and then they can vent out the CO2 because we can't still stop the CO2, but at least we can maybe stop this acid rain from happening. So at least they capture the acid rain in here in the scrubber part, and it's like they're scrubbing the exhaust of all the bad stuff, and then they neutralize it there on site. So this would be a practical solution that we now know of to prevent acid rain from entering into our atmosphere. I again found a handy YouTube video for how a sulfur scrubber works for when you're burning coal. So if you wanted to search up exhaust gas scrubbers, you can see how they kind of work together in these large industrial processes. If you search it up, and you can see how when they take the coal, how they can scrub out that sulfur, because they can't take it out like they can with natural gas, because natural gas is a gas and they can remove certain compounds before they burn it. Coal, well, it's all locked up as a solid, so they have to do something extra. And so it's kind of neat to see how these scrubbers actually work to help get a cleaner exhaust. So with acid rain getting cleaned up, we are talking about corrosion, because this corrosion still happens. There is still acid rain getting released, and there is still this big issue of what happens when we see iron mixing with this oxygen gas and turning into iron oxide. That's just the example of rusting. This corrosion is very dangerous. But why is it such a big deal? Why are we talking about it? What do we need to know about it? Why is rusting such a big deal? You can see here, this car would look a lot better if it wasn't rusted, might be able to work if it wasn't rusted. A lot of buildings could still be functional if they didn't rust out and get worn away. I would not want to be driving a car over these bridges or having trains drive over them, because we know as this rusting happens, this iron or this metal becomes more and more brittle, making it less able to hold up to things. And a lot of our structures, a lot of our buildings are made out of iron. And so that's why rusting is such a big deal, and this acid rain and why trying to stop it is such a big deal. So how do we stop it? Aside from stopping acid rain, which is hard to do right now, but how can we stop it? We're going to talk about a couple different ways to actually help prevent rusting from happening. One, you can coat it with paint, and paint creates a barrier from the oxygen actually reacting with the steel. This is why cars always have a nice paint job on them. And as soon as you get rock chips, why rust starts popping up right away? Because, well, water is all around us right now. As you can see, the snow, and there's road salts, which helps speed it up and help this reaction. And so, yeah, painting works, but it gets chipped away, unfortunately. Another way is called galvanizing. And so this is like painting, but to the molecular level. And this is where a thin layer of something maybe like zinc is applied chemically to the surface of the metal to actually protect it. And so they've actually bonded and attached some of the zinc so it's very unreactive to it. You would see this on a lot of fence posts, or that silver chain link fence is galvanized steel. And so they've actually coated it, and it kind of looks dusty, chalky, because that's what happens when zinc reacts to oxygen in it. It doesn't flake away, rather it creates kind of a chalky looking color, and that helps it actually prevent the steel from underneath from getting rusted. Not so desirable to have that as a car color though. Another way is when we can't actually access it, and if things needed to be replaced, there's something called a sacrificial metal. And so you don't want to be changing out buried underground pipes, whether they're carrying natural gas, whether they're carrying electrical lines. You can't just easily replace these pipes when they start rusting and corroding, and you don't want them to rust or corrode depending on what they're carrying. They might use something called a sacrificial metal, where something like magnesium corrodes even faster and better and will react. And knowing electrons, they always go for the easiest path, the path of least resistance. So they'll react with the magnesium first, saving the steel. So that's why they're a sacrificial metal. They're going to sacrifice themselves. This is also used on the inside of hot water tanks. There's a sacrificial rod to corrode inside of your hot water tank, so your actual hot water tank doesn't leak and, well, make a big mess wherever it is. So we got to the end of chapter 4. Woohoo! Yay! And now we're getting ready for our unit test. So remember, we have our key terms from this chapter. So make sure you go through them, make sure we're knowing all these little details. But also remember, review chapters 1, 2, and 3. The unit test will cover all 4 chapters of chemistry, and you can use all 4 of your study sheets that you've created to date to help you remember some of the little details. For now, practice your assignments. Make sure your study sheet has all these little details set up in them, or any little pictures or graphics or formulas that you might need. And good luck and have fun on the quiz.